Math 287, Cuesta College. I'm Joe Vasta, and we are going to cover, strangely enough, 9.4. That is the first section in Chapter 9 that we're going to cover. We'll come back and do 9.1, but this order seems the most logical for me, and this is called First Order Linear Systems. So let's go ahead and take a look at a first order linear system. There's one right there. And notice that our independent variable is t now. So we're going to be working on t. And you know, instead of having our other variables be x and y, we're going to call those other variables x1 and x2. And what we're going to be doing now, this is a system of differential equations. And with this system, it's kind of general because it has B1 and B2, and I didn't tell you what those are. But what we'll be doing is we'll be solving for x1, find out what function that is, and it's going to have t's in it probably, and x2, we're going to find out the x1 and x2 functions that will satisfy that system. So it's kind of like systems of linear equations that we did in linear algebra, except our answers are going to not be numbers, you know, like x1 equals 5 and x2 equals 7, but our answer is going to be more like x1 equals the sine of t and x2 equals like e to the 3t. Okay, so we're looking for functions. Let's go ahead and go over some definitions here. Normal form means that the derivatives are on the left-hand side, and that's what we have here. So this is in normal form. You don't see any derivatives on the right-hand side, do you? Okay. Constant coefficients, we've seen that before. Constant coefficients means that these coefficients right here in front of the xi's are all constants. You know, we don't have a t times x1 plus sine t times x2. That would not be constant coefficients. And the last thing we're going to look at is homogeneous. Homogeneous, this linear system will be a homogeneous linear system when the bi's are 0. And so you might think, well, homogeneous, I thought 0 was on the right-hand side. Well, if you bring all the x1s and x2s on the left-hand side with the derivatives, then you will have zeros on the right-hand side. Let's take a look at this system in a different light, okay? So if we know the variable we're taking the derivative with respect to is t, then instead of going dx1 dt, which is a lot to write each time, we can write it as x1 prime. And same with dx2 dt is x2 prime. Knowing that everything is a function of t, we're taking the derivative on t. And then the right-hand side looks like this. And now what I'm going to do is I am actually going to make this a homogeneous linear system. So let's go ahead and solve this linear system. Usually I would not do PowerPoints on things where I'm solving. I'd like to show you how to do things by hand. There are some exceptions. This one's going to be an exception because this is going to be kind of a clumsy way of solving it, and then we'll come back and do it by hand, a more efficient way. So let's take. Okay. So we have this system here, and we're going to solve this system normally like we would solve, you know, the very first linear system you had when you were in an algebra class. You're going to solve for one of these variables, either x1 or x2. Now the one that makes sense to solve for is x1 in the last equation, because then you won't get any fractions. But you don't need to do that, but that's what I'm going to do. So when I solve for it, I end up getting x2 prime minus 2x2. What I'm going to do now is I'm going to plug this into the first equation for x1. So let's do that. And so here's an x1 prime, and then there is an x1 there. So let's see what that gives us. So everywhere there was an x1, I put an x2 prime minus 2x2, because that's what it is there. So there was one right there, and then we're taking the derivative of that, and then we have 3x1, so that's what that is, plus 2x2. So I'm going to go ahead and take the derivative of the left-hand side. The derivative of everything's with respect to t of x2 prime is going to be x2 double prime, and the derivative of minus 2x2 is going to be minus 2x2 prime. And then I'll distribute the 3 on the right-hand side of the equation. So I end up getting something like that. Now notice that all my variables, they are x2, t's there in the background, okay? But I have derivative of x2, second derivative of x2, and all the x1s are gone. So I'm going to go ahead and bring everything to the left-hand side of the equation. And when I do that, you might notice that this is just a single differential equation, homogeneous, constant coefficients. So I can write out the auxiliary equation, which looks like r squared minus 5r plus 4 equals 0. I'm going to factor that into r minus 1, r minus 4. And I get two r values, 1 and 4. Now what I'm going to do is write out the solution to this single differential equation here. It's going to say x2 equals something. So what does x2 equal? It equals c1 e to the t plus c2 e to the 4t. So just in the context of what I'm circling here, so I'm going to loop this, just in the context of this was just a single differential equation that we already learned how to solve. Now, we're not done solving this system up here. The system's going to have two things. It's going to have x2 equals and x1 equals. So now I'm going to take this x2 and plug it up here to find out what x1 is going to be. So when I do that, everywhere there's an x2 in that equation, I'm going to replace it with that expression with the c1s and c2s. And so I do that. So here is x2 and then prime, so I have to take the derivative of that. And then I have minus 2 times that. So let's take the derivative of c1 e to the t. That's going to be c1 e to the t. And the derivative of c2 e to the 4t, there's a little chain rule there. It's going to be 4c2 e to the 4t. And then I'll distribute the negative 2 on the other part. I'm going to go ahead and combine like terms. I have a c1 e to the t and a negative 2c1 e to the t, which gives me a negative c1 e to the t, and I'll do the other part too. And I get this expression here. Now, some of you might be tempted to go, aha, let's just let negative c1 equal c1 and 2c2 equal c2. The problem with that is over here you have a c1 and a c2, and if you were to do that over here, that would affect the value of c1 and c2 in this equation right here. So we're not going to do that. We have solved the system of differential equations, our very first one, and let's go back and rephrase our problems and look at the answers and do something kind of neat. So here's the next PowerPoint slide. So here was, we'll call this problem number 1. And we had a system of differential equations, and then we found the solution by doing substitution. Okay. So what I'm going to do is I'm going to repackage this system of differential equations. Just like in chapter 2, when we were doing linear algebra, I repackaged a linear system, just a regular one. So I'm going to repackage it using matrices. And there it is. So this is x1 prime, x2 prime. And then over here, look at this is pretty clever. We have the coefficients, which make a coefficient matrix, 3, 2, 1, 2 multiplied by the vector x1, x2. And if you do the multiplication out, like 3x1 plus 2x2, that gives me the top part right there. And you get the bottom part by doing the other part of the multiplication. So you can see we've just repackaged our system of differential equations, and we can go ahead and sell it to the same sucker who bought this one, and he won't even know he's buying anything that's the same. So because we like this notation, we're going to go ahead and, this is x1 prime, x2 prime. If we were doing a bigger system, this vector might say x1 prime, x2 prime, x3 prime, x4 prime, x5 prime, x6 prime. Hopefully we won't have to do anything like that in our homework. But anyway, it's going to have all your xi primes. So we're going to call this vector x prime. We're going to call this matrix here, the coefficient matrix, A. And then we're going to call this vector, which is x1, x2, but it could have x1, x2, all the way to x6. We're just going to call that vector x. So our repackaging looks like this. Now, if I were writing this on the board, and you'll see me do this when I do some problems by hand. You'll see me, we don't do bold when we're writing things out by hand. We would put a line over that x, and then we'd still have to put the prime. So it gets a little crazy. This right here is called a vector differential equation. So we are solving a system of differential equations, but we could also say that we're solving vector differential equations, VDEs. Okay. Now what we're going to do is we're going to take a look at our solution. Our solution can be written repackaged as matrices. So let's do that. So x1, x2, we already know what x1, x2, it's vector x there. So let's write that. So vector x is x1, x2, and it equals these two things. Okay, you can verify that equals that. Okay, so I'm going to do something strange. Okay, it's not okay. So just to get the point straight, I'm not solving this problem anymore. I've already solved this problem. What I'm doing is I'm just introducing notation and more efficient ways of writing things. So what I'm going to do is going to trip some of you out. I'm going to split this matrix up. I'll put my e to the t's in one matrix and my e to the 4 t's in another matrix, and then I'll even factor them out. So I'm doing some algebra, some matrix algebra here, and I end up getting, that's the same C1 you see there, C1 e to the t negative 1, 1, plus C2 e to the 4t 2, 1. Okay, now this vector right here that says e to the t negative 1, 1, that we're going to relabel that as vector x1. And then over here, we're going to label this one e to the 4t times 2, 1 as vector x2. And those vectors are going to be in bold here. So look what I have. I have x equals c1 x1 plus c2 x2. Now, what does this remind you of here? And it starts with an L. Well, that's a linear combination. It's the linear combination of two vectors. In fact, this is a subspace of V2. And since we solved a homogeneous system of differential equations, what we really did is we found the kernel of some linear transformation. Now, without confusing people too much, let's go ahead and tell you what V2 is. V2 over an interval is the set of all two vector functions defined on the interval I. V2I is actually infinite dimensional vector space, but this guy right here, this is a subspace that has dimension 2. So notice this right here, what did I write right here? It says a subspace of V2. Okay, x1 and x2, those vectors up there, are independent vectors from V2. And any two independent solutions can form the general solutions of your vector differential equation, because if you have any two independent solutions, then they form a basis, and now we're getting back into the linear algebra, and you end up getting a general solution. So sometimes that vector x1 and vector x2, if you put them in a set, it is called the fundamental solution set. And in fact, this is important for our derivation on the next slide, is that those guys each satisfy the vector vector differential equation. So if you just put that red part right here into this vector differential equation, it would make it true. And if you just put this red part in, it would satisfy it. Or if you put any linear combination of those guys in, it satisfies our vector differential equation. So that's what that says. Now I think it's time to go to the next slide. And what we do on the next slide is going to be incredible. It's going to bring linear algebra together with the differential equations. So here it goes. So there's problem one. This is the repackaging, so that's what it looks like. And here's the solution, which is repackaged, c1x1 plus c2x2. And now we're going to do some busy work. This is a busy work right here. I hate when they do this. When I was a math student, I hated these problems. Verify that x2 satisfies the vector differential equation. So that's what we're going to do. We're going to put x2, which is this guy right here. I just picked him. Okay, I could have picked x1. I'm going to plug it into this vector differential equation. In order to do that, I must take its derivative. So x2 is e to the 4t, 2, 1. So I'm just copying it down. The derivative with respect to t, well, 2, 1 is just a constant. And so the derivative of e to the 4t is 4e to the 4t. And so we have that. So now I'm going to plug that into the vector differential equation. And this blows your mind, I'm really working with systems of differential equations. It's crazy, isn't it? Okay, so I have x2 prime, that vector equals ax2. All I did was plug x2 up there into that. And let's see what happens when we do this. x2 prime is 4e to the 4t, 2, 1, and then there's a, and then this is x2 is just e to the 4t, 2, 1. I'm going to go ahead and put a there. Okay, so we know what a is. So that's what I did. I'm going to go ahead and bring the e to the 4t over to the left side because it's just a scalar when it comes to matrices. And I'm going to multiply the matrix 3, 2, 1, 2 together with 2, 1. And I'm going to get 6 plus 2, which is 8, and 2 plus 2, which is 4. And then I'm going to go ahead on the left-hand side, I'm going to bring that 4 into that matrix. And look what I end up getting. Verification is done. Okay, so I like the math problems where you're actually trying to find a function or find the answer to a question instead of just like, hey, do this busy work, verify that this is true. Okay, now we're done with this problem here that they asked us to do. But now I'm going to go back up here where the red circle is and look at that equation. Both sides have an e to the 4t. And that e to the 4t can never be 0. So I'm going to divide both sides of that equation there by e to the 4t. And look what I end up getting. I end up getting 4 times vector 2, 1 equals a times vector 2, 1. Does that remind you of anything? From linear algebra, when you have a matrix times a vector equals a scalar times the same vector, why, that should remind you of eigenvalues and eigenvectors. In fact, 4, 2, 1 is an eigenvalue eigenvector pair of a. This is not a factorial, okay, so this is just because I'm excited. Does it sound like I'm excited? No, I'm just pretending I am. Okay, but it is an eigenvalue eigenvector pair for this matrix A. And guess what? Could you, I know we didn't find the eigenvalue eigenvector pairs of that matrix, but could you just guess what another eigenvalue eigenvector pair of A is? Just by what we see here and what we see there. Maybe your guess would be 1. Negative 1, 1 is another eigenvalue eigenvector pair of A. So that's pretty neat because remember when we did substitution to solve this problem and get the solution? it was pretty clunky, it was pretty inefficient, and especially if we had a 3x3 matrix, it would be super tedious. So instead, what we can do is find all eigenvalue, eigenvector pairs for this matrix that they give us that is associated with our system of differential equations. And after we do that, we can just write out our answer by going e to the eigenvalue times t times any eigenvector. So I could have chosen, instead of -1, 1, I could choose -5, 5. Of course, my C1 would absorb that scalar. So let's take a look at the next problem. Problem number 2. Let's solve this system of differential equations. Now, before I solve it, I'm going to do something a little optional that you don't have to do. I'm going to write out what this is. Remember that this x bar prime is really x1 prime, x2 prime, as they call them vector. And then here's a, so what I'm doing in blue is optional. And then what is vector x? Vector x is x1, x2. So if you multiply out the right-hand side, you end up getting 4x1 minus 5x2 for the top entry of that matrix. And then over here we get 2x1 minus 3x2 for the bottom entry. And then this one right here says x1 prime and x2 prime. Let me just write this out so it looks kind of nice without the matrices. This is x1 prime equals 4x1 minus 5x2. And then this is x2 prime equals 2x1 minus 3x2. So our system is right there. The problem could have been written out like this. And if it was, I would first grab matrix A, which you can easily see that's what it is, and do what I'm about to do. So this right here was optional to write down. What I'm going to do is solve this using eigenvalues and eigenvectors. So now it goes back to, do we remember about eigenvalues and eigenvectors? Well, here it goes. The first thing you want to do is go a minus lambda I. And so this gives me 4 minus lambda, -5, 2, and -3 minus lambda. I'm going to go ahead and take the determinant of that matrix, and I end up getting lambda squared. And we have -4 lambda plus 3 lambda, so that's minus lambda. We have -12. Okay, so I just went AD, and a minus BC, that's plus 10. So this gives me lambda squared minus lambda minus 2, and I'm going to set this equal to 0. This right here is my characteristic equation. I'm going to factor and solve for lambda, and that's going to give me my eigenvalues. My eigenvalues, let's see, a 1 and a 2, and probably a plus there and a minus there. And so I end up getting eigenvalue -1 and eigenvalue 2. Okay, so lambda equals -1. I plug that into the A minus lambda I matrix that I have right there, and I end up getting 4 minus a -1, so I have 5, -5, and then 2, -2. And what am I trying to do with this matrix here? I'm actually trying to find the null space of that matrix. So sometimes you might remember in the other lectures I'd put red dots there and say here's x and here's y, and y equals t, and what does x equal? When I have a 2 by 2 matrix and there's no imaginary numbers in this, I just try to zero out the first row. If x is 1 and y is 1, I have 5x minus 5y, so that would zero that out. And so now I know my eigenvectors are going to look like t times 1, 1. But I'm just going to pick up any eigenvector. So I just need that one. So I'm going to go ahead and find the eigenvectors for lambda equals 2. A minus lambda I. I'm trying to find the null space of that. And so this gives me 2, negative 5. The bottom one's going to say 2, negative 5. And finding the null space here, because we've done this many times, I'm not going to write out all the steps, but something that will zero out that first row would be if x is 5 and if y is 2. So my eigenvectors are going to be t times 5, 2. Wow. So that gets the job done, and now I'm ready to write out my solution. You're going to see that in some of your homework problems that most of the work is doing linear algebra, eigenvalue, eigenvectors. So watch, here's the final answer. The final answer is x bar equals C1, and then we go with this eigenvalue, eigenvector pair. Let me box these here. So I have C1 e to the negative t, and then we have vector 1, 1. Okay, plus C2 e to the 2t, and then any eigenvector that goes along with that eigenvalue is all right. I'm just going to pick 5, 2, but you can pick 10, 4 if you want, or any multiple of it. So I'll just say 5, 2. Now there was a little memorization going from here to here, but look at this. Most of the work was what? Finding eigenvalue, eigenvector pairs. So we are done with this problem, but because I'm a little bit of a math nerd, I'm going to go ahead and analyze this. Like, how would this look? I mean, it doesn't feel like we're looking at the solution to a system of differential equations, but this right here, vector x, is really x1, x2. And if we write out x1 and x2, I'll write out x1 traveling along the top part. I end up getting c1 e to the negative t, that's the top part, plus, and then there's a 5 there, so I'll put that in front, 5 c2 e to the 2t. And the bottom one's going to be c1 e to the negative t, because there's a 1 there, 1c1, and then this is going to be plus, I'll put the 2 out front, plus 2c2 e to the 2t. And so here was the original problem. I mean, the original problem was up here, but if written like this, and then look, we have just solved for those two unknown functions, x1 and x2. Really, it's x1 of t and x2 of t, and that's what they are. And this right here gives me a solution. There's the general solution. Now, when you're doing your homework and they give it to you with a matrix, this right here is acceptable to write your answer like that. It's just packaged up. So we'll go back to the PowerPoint, do just a little bit of theory on this problem, and then the rest of the lecture will be me writing out problems. Okay, so we just finished problem number 2, and that was the solution that we got for problem number 2 when we find the eigenvalue eigenvector pairs, and this is what you'll be doing in your homework. Now, we brought it back to the PowerPoint because I wanted to throw a little more theory at you, and then show you some really cool pictures. And then we'll spend the rest of the lecture just on the piece of paper, me writing things out. So some theory. Our solution to this looks like C1x1 plus C2x2. Let me see if I have the laser pointer. Oh, there, it's back. Okay, so I have that, and that's what we have written there. Okay, what I'm going to do is I'm going to do something. So we're done solving problem 2, but we're just looking at some theory. I'm going to rewrite this as a row vector times a column vector. And you can see it really does say C1x1 plus C2x2. Now notice, even though this does look like a row vector, these are vectors. X1 is actually e to the negative t, and then right below it is e to the negative t, and then x2 is 5e to the 2t, and then below it is 2e to the 2t. So this, even though it looks like a row matrix, it's actually a 2 by 2 matrix in this example. And that's where all the information is. And so what I'm going to do is I'm going to replace that matrix that is right above the red circle with an x. X marks the spot. Look at that. And so I have x times C1, C2. X has a special name. It's called the fundamental matrix. And so let's write out the fundamental matrix. The fundamental matrix is really this right here. I think I said it. It happens to be the things that are in red there on the top right. So it's that 2 by 2 matrix. Now, it just so happens that you can take the determinant of that 2 by 2 matrix, and that determinant, you go AD minus BC, what you end up getting is you end up getting negative 3e to the t. But that's going to be important later on. You won't be doing this in the homework from 9.4, where you're going to be writing the fundamental matrix and taking the determinant. But we have done things where we've taken determinants of matrices that had functions in them. And this might remind you of the Wronskian, but it's not really the Wronskian we learned. Our Wronskian, on the first row, we would have 2 functions, which we have. But the second row would be their derivatives. And obviously, the second row is not derivatives of the first row. Now, having said that this is not our Wronskian that we learned, it's actually still called a Wronskian, and I'm going to call it the Wronskian of the second kind. So this determinant of the fundamental matrix is called the Wronskian of the second kind. Now, what we can do is we can say that that Wronskian does not equal 0 on the interval from negative infinity to infinity, or just any interval. It does not equal 0. And because of some theory we had before from linear algebra, we can conclude that x1 and x2 are linearly independent. So there's talk in your book about this. You don't have to do this in 9.4. And here's the other part. If you use the eigenvalue eigenvector method that we just used to solve problem 2, then there's no need to check for independence. Okay, so that's great. You're probably wondering, well, why are you telling us about the Wronskian of the second kind? Because that's going to come up when we do vector differential equations that are non-homogeneous. And that's coming in like 2 sections from now. And besides, in this example, since we only had 2 vectors, we only need to check to see if they are scalar multiples to see if they are independent, and they are independent. Before we get back to problems, you might be wondering, wow, we're doing these systems of differential equations. This is just a brief introduction to systems of differential equations, but where are they used? Coupled springs, where you have position functions of mass 1 and mass 2. Then what you have is you have 2 functions you're looking for. You have a system of differential equations. Circuits. Now we did the circuits and it just formed one rectangle, but now this circuit is a little bit more complicated and there's more than one loop. Well, that's going to yield a system of differential equations. Mixing problems that we did in chapter 1, we would just have a tank and water comes out. Now we have two tanks, and water's traveling between both of them, maybe what, a mixture, saline solution is traveling, and then it comes out there. This can be modeled using a system of differential equations. And the last thing for the examples that I'm showing you here is we never really studied pendulums in here, just because, you know, I didn't want your physics teacher to, you know, when he starts talking about pendulums saying, oh yeah, Vasta, he already told us everything about pendulums. So we never talked about pendulums in this class. But a single pendulum can be governed by a differential equation. A double pendulum, when you're kind of keeping track of both of those ends, well, then you would have a system of differential equations. So let's get back to cranking out more problems by hand. So back to the paper, and you might recognize this problem. This is the problem that we did, problem 2, and this was the solution. So I wrote the solution there. And what I'm doing on this one is I'm giving us an initial value. So it says when t is 0, we have vector -2, 1. And so I wanted to solve an initial value problem that was from the last problem, and then we'll go back and solve some other ones, finding eigenvalues and eigenvectors. Now, you also might recall that when I did this, I wrote down the problem. Here's what the system of differential equations. Here's the answer. So when you're given an initial condition, it says vector x evaluated at 0 is -2, 1. It's the same as writing this. x1 of 0 is -2, x2 of 0 is +1. You can see, hopefully, that those are the same thing. So you can actually use this blue part and find out what C1 and C2 equal. I'm actually going to use this right here. So let's see if we can do this. I'm going to plug this right into there. See what happens. Oh, a caveat. Your book, they will say x sub 0 bar for that. That's what your book will say. And that's cute and all that stuff. I mean, I've seen, you know, that's some notation. I like this better. So we plug these initial values into the general solution. And so really, what does this say? This says t is 0 and x bar is going to be -2, 1. That's really what it says. Or over here, you would say t is 0 and x1 is going to equal -2 and x2 is going to equal +1. So I plug that into this differential equation. So here it is. -2, 1. Let me extend this arrow here. So I'm writing up this equation, equals C1 e to the -0, 1, 1. I'm writing it all down because a lot of you are new with this notation. C2 e to the 2 times 0, 5, 2. Okay, this is -2, 1 equals, well, this is just C1, 1, 1 plus C2 times vector 5, 2. So really, this is kind of giving me two equations and two unknowns, the C1 and C2. Just going on the top road, I get -2 equals C1 plus 5C2, and then 1 equals C1 plus 2C2. I'm going to go ahead and bring this over here. I'm just going to go and maybe subtract. I'll go equation 1 minus equation 2. So this gives me -3 equals, the C1s are out of there, 3c2. So c2 equals -1. And then I can plug that back into the bottom equation or this top equation here, and I'm going to end up getting c1 equals, let's see, -2. We add, so that's going to be 2 plus 1, which is 3. So my final answer, this is a particular solution for this. See, this general solution right here, let me circle it, has many family members, which are vector functions, because c1 and c2 could be any real numbers. When I plug this initial condition in, I'm going to get one of the family members. And so here is a particular solution. This family member looks like this. I'll replace the c1 with a 3, e. So I'm just rewriting this general solution. So 3e to the -t, 1, and then I have plus c2 or minus e to the 2t, 5, 2. So that's how you take care of initial conditions if you're given them. You're not giving them that much in your homework, but when you are, then that's kind of what you do. I am done with this problem, but what I want to do is I want to go ahead and write out what this is, kind of like I did up here. This really says x1 equals 3e to the -t minus 5e to the 2t, and x2 equals 3e to the -t minus 2e to the 2t. So this right here is how you would write it if you were just doing the systems and writing it like that. So you might ask yourself, well, what just happened? What have we done here? Well, I'll tell you what we've done. Some of you might want to just skip ahead on the video, is when we have this, like a lot of computer graphing programs, you would have to enter this, and that's what I'm going to do. I'm going to enter this system of differential equations. It's first order. So lots of times you would have to say this is x, x1 is x, and x2 is y. And so you have like x prime equals 4x minus 5y, etc. And so when you enter that in there, what you have, so this is the differential equations here. So you'll see this, and I'll write them in terms of x, y's on here so you can see what I've done. Is I'll have a vector field. So if you've taken Calculus 3, you've seen vector fields. Now the lengths have been scaled and they're all the same length. It's just because the program that I have does that, but it doesn't really matter. You have some arrows. And when I am given this initial condition of -2, 1, that's like x equals -2, y equals 1, that is a point. -2, 1. Now you won't have to do this geometry when you're doing your homework, so there's the point -2, 1. There it is. Now, this vector field has many solutions going through it, and we found all the family members. The family members are all those guys, and so we can plug in different CI values, maybe C1 equals 7 and C2 equals -10. And that would be a curve, a parametric curve that goes and follows the arrows. So what we did is we found a parametric curve, x equals this, y equals that follows the arrows and goes through that point. So let me go ahead and show you what it was when I entered this into the graphing program. I ended up getting this one right here. Now that does kind of look like a line, but if I went back, zoomed back, it's actually curved a little. There's a little arrow, which means I'm going this way, and it hits the point. And so, yes, and that's what I entered into the computer program. So are there geometric ramifications of first order linear systems? Absolutely, and we don't have time to get into all those geometric interpretations, but they are very interesting. So this completes problem number 3, which was, it was problem number 2, and I threw an initial condition in, and we showed you how to find C1 and C2. Let's go ahead and do problem number 4. And there is an existence and uniqueness theorem that goes with systems of differential equations that I'm not going to go into now. So I think what I'm going to do next is problem 4. Problem 4 says solve this vector differential equation. That's what this is. It's really a system of 3 differential equations. Here's the matrix. This is where all the information is. So when you go to do your homework in 9.4, you'll open up your book. If you go right to the homework problems, which most people do, you're going to see for the instructions to solve something like this, and then each of your problems is just going to give you a square matrix. You're going to feel like you are in linear algebra again. And in fact, like 95% of this problem, I'm just making up that statistic, is stuff that we did in linear algebra. But you know, it's worth going over. I'm gonna go ahead and see if we can do this. How do I solve this? I find all eigenvalue, eigenvector pairs, and then I'm just gonna write down the answer from that. So you could pause the video and see if you can do the problem. And I'll start right now. So to do this, I'm gonna find out what A minus lambda I is. A minus lambda I gives me negative lambda 0, 2. Negative 1, 1 minus lambda 2. Negative 1, 0, 3 minus lambda. Okay, so there it is. And what am I going to do with this? I'm going to go ahead and take the determinant. So A minus lambda I, it's the determinant, and to take the determinant, I think I'm going to go ahead and travel down the middle column. 1 minus lambda is in the positive position, and so now I'm left with, what am I left with? Lambda squared, I'm computing the minor, minus 3 lambda, and then plus 2. So what do we have? I'm going to factor a negative out of that first one just so it looks nicer. Lambda minus 1. And then over here I have, what is this? This factors into lambda minus 1, lambda minus 2. So lambda minus 1, lambda minus 2. So this gives me negative lambda minus 1 squared, and then we have lambda minus 2. What do I do with this excuse me, characteristic polynomial? I set it equal to 0, and I end up getting my eigenvalues of 1 and 2. The eigenvalue 1 has algebraic multiplicity of 2. The eigenvalue 2 has algebraic multiplicity of 1. Let's go ahead and go lambda equals 1. When I say lambda equals 1, I'm going to plug it back into the A minus lambda I matrix. And I end up getting negative 1, 0, 2. Negative 1, 0, 2. Negative 1, 0, 2. Okay, that one's pretty easy, so that will, we'll get 1, 0, negative 2, 0, 0, 0, and everything else is zeros. And what am I trying to find on this matrix? I'm trying to find the null space. So I'll work this one out a little. Here's x, here's y, here's z. Z is t, y is s, and the first equation gives us that x equals 2t. So the set of eigenvectors that goes with this eigenvalue would be this right here. We have 2t, s, t, I'll splactor that. So I'll have s times 0, 1, 0 plus t times 2, 0, 1, where s and t are both not 0. And it's these vectors that I'm after. In fact, we see with lambda equals 1, you have algebraic multiplicity of 2, and geometric multiplicity is also 2. So this is a good thing. Lambda equals 2. So a minus lambda I equals, let's see what we get on this one. This is going to be negative 2, 0, 2, negative 1, we're putting 2 there, so negative 1, 2, and the last one's going to be negative 1, 0, 1. Okay, I'm going to go ahead and make this right here, negative 1, 0, 1, my first row, because that, row 3 and row 1 are scalar multiples of each other, so I'm just going to go 1, 0, negative 1. Look at this. Here we are doing differential equations, and it all comes back to what? Linear algebra. I'm going to go ahead and subtract row 2 minus row 3. That gives me, let's do it the other way, row 3 minus row 2. So 0, 1, negative 1. And then I have zeros there. What am I trying to find on this matrix? The null space. Here's x, y, and z. So I have that z equals t, and from the second row I get y equals t, and from the first row I get x equals t. So this is t, 1, 1, 1. So we have that right there. We can also see that the algebraic multiplicity equals 1 from right up there, and the geometric multiplicity equals 1 because we only have one parameter. And that would actually show you that this matrix A is non-defective. Okay, so let's go ahead and piece together our answer. What is our answer going to look like? Well, because this is a 3 by 3 matrix, we're not just going to have C1, C2, we're going to have C1, C2, C3. The vector space we're looking for is going to be the linear combination of 3 vectors. And so here it goes. Let's start off. X bar equals. Let's go start off with lambda equals 1. There's 2 independent eigenvectors that we can use. So the first thing is going to say C1 e to the eigenvalue, which is 1 times t, and then we multiply that by one of the eigenvectors, 0, 1, 0, plus C2 e to the t again, because we have more mileage, we have another independent eigenvector, which is 2, 0, 1. So we have 2, 0, 1. Plus, now we're going to do C3 e to the 2t, and then we use this eigenvector, which is 1, 1, 1. We write it right there, and we end up having our solution right here. And we can write out all the solutions. I mean, this is really x1, x2, x3, and x1 equals 2c2 e to the t plus c3 e to the 2t. And we could also write out the other thing, the things that I was doing in blue, but we don't have to do that for this problem. We are finished with this problem. And do you see that on this problem, that most of the work was done where? It was done finding eigenvalue-eigenvector pairs. Also note that A is non-defective. 9.4 is going to deal with first order linear systems where the matrix is non-defective. 9.5 is going to deal with first order linear systems where the matrix is defective. And so we don't know how to do it. Like if this was defective and this one only cranked out one eigenvector times times t, then we wouldn't know what to do. And some of you might think put an extra t in. We're gonna see what happens in 9.5 when we get to there. Let's do a few more problems from this, and this is what you'll be doing in your homework. Number 5. So number 5 is when we went back to a 2 by 2 matrix. So let's go see how we would solve this equation here, or solve the systems of differential equations. The first thing you want to do is you want to compute the eigenvalue eigenvector pairs. So we have A minus lambda I equals 6 minus lambda, -1, 5, and then we have 4 minus lambda. Okay, so what I want to do now is take the determinant of that, and when I do that I end up getting lambda squared, then we have -6 lambda minus 4 lambda, so that's -10 lambda, then we have plus 24, and then plus 5, so that's going to be plus 29. And when we go to factor this over the rational numbers, we're not able to do that. So what we have to use is because we're setting this equal to 0, we have to use the quadratic formula. So negative boy couldn't decide on a radical party. He was a square. He lost 4 awesome chicks. So 4 times 29 times 1, 36, 8, 9, 10, 11. I don't have my calculator with me, so I'll just do that. And then the party was all over by 2 a.m. So this gives me 10 plus or minus square root of -16, which is 4i. This is all over 2. We split the fraction and we end up getting 5 plus or minus 2i. So those are the eigenvalues. Okay, so we have lambda equals 5 plus 2i. Let's go ahead and see what a minus lambda I is. A minus lambda I. And we plug them in. Now I know we're doing some imaginary numbers, and so that gives some people a headache, but let's see what we get. We get 6 minus this, so that's going to give me 1 minus 2i right here. Then I have a -1 and a 5, and then I have 4 minus this, so this is going to give me -1 minus 2i. What am I trying to find on this matrix? I'm trying to find the null space. And because this was an eigenvalue, I know that these two rows are multiples of each other. You can verify that on your own, but I'm just going to go ahead and take the first row. That's the one I'm going with. 1 minus 2i, -1, and then 0, 0. So we'll do that. If you multiply the top row of this by 1 plus 2i, you'll end up getting that, and then you'll get 1 plus 2i times 1 minus 2i. Difference of squares, it will be 1 minus 4i squared, which is 1 plus 4, which is 5. So I verbally verified that those were multiples of each other, and some of you are like, say what? What did you just do? I'm going to go ahead and put some zeros there. I'm going to call this x and call this y. And I'm actually going to break convention. I'm going to say that x equals t. And so what do we have? We have 1 minus 2I times t minus y equals 0. So I'm going to get y equals 1 minus 2I times t. So the set of eigenvalues looks like this. It looks like t times this, 1 comma 1 minus 2I. I'm not going to put the t times, but there it is. So this gives me eigenvalue, eigenvector pair. Now we'll call this lambda 1 and we'll call this v1. Lambda 2 is 5 minus 2I, and its eigenvectors kind of look like this, multiples of, we just take the complex conjugate of each of these. The complex conjugate of 1 is 1. The complex conjugate of 1 minus 2I is 1 plus 2I. So we have what we have there. So a lot of you might say, let's go like this. We can write out our solution, our general solution. We have x1 bar, which would be e. Now this is going to get a little weird. To the lambda 1 t times v1. So here's lambda 1 and here's v1. And then x2 bar equals e to the lambda 2 t times v2. Okay, where what is our solution? It's going to be x bar equals c1 vector x1 plus c2 vector x2. Okay, so that's really our solution. Now, this gets really messy because what we have here for lambda 1 is imaginary numbers, and for lambda 2, imaginary number. v1 and v2, they're both filled with imaginary numbers. So this is going to be really ugly. Now, I've seen some textbooks say, okay, let's go ahead and write this all out and do Euler's formula. And the whole idea is to get rid of all your imaginary numbers and maybe absorb them into the constants. So here is a trick. And this trick will always work. x1 bar, which is, what's x1 bar? It's this right here. Okay. So I know this is a mess, and we'll actually, on the next page, we'll write things out more. x1 bar can actually be ripped apart into two vectors. The first vector called xr bar, which is cool to say, xr bar, which doesn't have any imaginary stuff in it, doesn't have any i's in it. And the second part we'll call xi bar, which does have the i's in it, but I'm going to factor the I out front, so it looks like that. So x1 bar equals xr bar plus ixi bar. This is where the theory of linear algebra really comes in handy. Okay, the theory says that when you have a solution that any two independent vectors that solve the vector differential equation will work in the general solution. So x1 and x2, x1 bar and x2 bar both solve this vector differential equation, and they are independent. Therefore, we have a good general solution. But here is the cool part. xr bar, I'll circle it in blue, and xi bar, we're not going to prove this, but those guys are independent vectors, and not only that, they each satisfy the vector differential equation. Maybe I should write that down. So these guys, meaning vectors, each satisfy our original vector differential equation. Okay, that's just, there's a theorem that says that. And these guys are linearly independent. So we only need to grab onto one eigenvalue-eigenvector pair to get the answer. And because we can make the same argument with if we had picked x2 bar. But I'm going to pick x1 bar. And on the next page, you're going to see me physically break those apart. And then I will, in blue, circle xr bar, xi bar, and then our answer is just going to be that, except not with the green, but with the blue. And it's kind of a clever way. We are using linear algebra to the extreme to save us some algebraic work. Okay, so the book's going to give us formulas. They're going to say, here are some formulas to remember. And the formulas could even be a little confusing to apply. The only formula we have to remember is this one right here. E to the I x e to the ix equals the cosine of x plus I sine x. So that is the only formula that we're going to apply to this. So let's go ahead and write out what x1 bar is. So x1 bar is e to the eigenvalue, which is 5 plus 2i t times the eigenvector, which we're going to write like this, 1 and then 1 minus 2i. Okay, so all I'm doing on this is algebra. We are going to, so here's our goal. So x1 bar, I'll write it again so we can see it on this piece of paper. We want to rip it apart so it says xr bar plus I times xi bar. That is my goal. So can I rip this apart? Yes, I can. Okay, the first thing that I'm going to do is I'm going to use the property of exponents to write this as e to the 5t times e to the 2it times this vector here, 1, 1 minus 2i. Okay, so now what I'm going to do is I'm going to use, we'll circle the Euler formula in orange. I'm going to use that right for this here. Playing the role of x is 2t. So when I have this, I have e to the 5t. Then we have the cosine 2t plus I sine 2t. And then we have this vector here who's not doing much right now. Okay, so we've just used the Euler identity. Now I'm going to go ahead and bring that orange part into that matrix. The e to the 5t is going to stay outside, and on the inside we have 1 times that orange thing, so this is cosine 2t plus I sine 2t, and then the bottom part I have to do a FOIL. First, cosine 2t times 1. Outside, cosine 2t times negative 2i, so this is negative 2i cosine 2t. Inside, which is I sine 2t times 1, so I sine 2t. And then last, which is negative 2i squared sine 2t. Okay, the next thing I'm going to do, and I could have actually skipped this step if I knew what I was going to do, but I'm just kind of playing this like we've never done one of these before, is I'm going to kind of put my non-i's sort of on the left and anything that has an I on the right. Now before we do that, we do have an I squared here. And what is I squared? I squared is -1. So this is -1 times -2, which makes a +2. So I'm going to say this. I'm going to say to these terms, okay, everything, okay, the top one's pretty easy. I'm going to put the cosine 2t on the left, leave a space, and I'm going to go I sine 2t. On the bottom, I have a cosine 2t, and then the other thing that does not have an I is this one, that is the purple one here, 2, so we have plus 2 sine 2t. Now the ones that have an I are these guys right here. And what I'm going to do even more is I'm going to go put the I here, and I'm going to just write it like this. And you don't really have to write it like this, so I have a sine 2t, sine 2t. I'm writing them in another order, I guess, and then minus 2 cosine 2t. And so see what I did? All I'm doing is algebra, and I've kind of separated it out like that. The next thing that I'm going to do is I'm going to break this up into 2 vectors. So let's go ahead and do that. This gives me e to the 5t, and then what do I have? I have, this one is the cosine 2t. This is the cosine 2t plus 2 sine 2t. And then this one is plus I sine 2t, I sine 2t minus 2 cosine 2t. Okay, now my goal, okay, so I've kind of covered up my goal here. My goal is to have this right here, to this guy's x1 bar, is to write x1 bar like this, and I almost have this. So what I have is, I'm going to multiply, distribute that e to the 5t, so it looks like e to the 5t times that first one, cosine 2t, and I'm getting sick of writing these again and again. As you do more of these, you will skip steps probably. You'll say, oh yeah, I know I have to collect those and put those over there. And then I'm going to go like this. So I'm going to actually factor an I out of that matrix. So it looks like this, plus I, e to the 5t, then we have sine 2t, and then this is sine 2t minus 2 cosine 2t. Whew. So did I achieve my goal? Yes, I did. This is x1 bar equals, here's xr bar plus I times xi bar. And we said, well, these are 2 independent vectors that satisfy the vector differential equation. So I can write my answer like this. So my final answer could be C1. Well, let me write this out first. This is XR bar, and this is XI bar. So I can write it as C1 X1. Okay, let me just write it here. C1 XR bar plus C2 XI bar. And so that's what I'm going to write it as. So X bar is C1 e to the 5t, and this vector that I'm getting sick of writing again and again, cosine 2t, and then cosine 2t plus 2 sine 2t, and then we have plus C2 times the blue part. So we're not going to write the I there. E to the 5t sine 2t sine 2t minus 2 cosine 2t. And so this gives me the answer. Now, the other eigenvalue-eigenvector pair would have, if you did the other eigenvalue-eigenvector pair, it would have, I think this would have been the same, and then this would have been a negative and a positive and a negative, which is actually just a scalar multiple of this one right here. If you went ahead and did what some books do, some books will do this and they'll do Euler identity on both of these, which is a real algebraic mess, and guess what you end up getting? You end up getting the same answer. And sometimes if you look up your answer and it appears to be a little different, all it is a different parameterization of the same family of curves. So that is how you do these problems. We're pretty much good in terms of 9.4, in terms of we've covered everything. Let me go ahead and just cover one more problem, problem number 6, and I think I took it from one of the homework problems, or an uneven problem. And here it is. Solve this matrix here. Solve this, sorry, I keep saying that. Solve this vector differential equation. And I'm going to actually just say, okay, I'll tell you what the eigenvalue-eigenvector pairs are. So lambda is 5, and it has an eigenvector of 0, 0, 1. We have lambda is I, and it has an eigenvector of 1, I, 0. And then we have lambda is, well, we didn't even have to do the lambda as negative I, but you could probably fill in what that is. I'm not going to write that out. Okay, so we know how to write the answer for this one right here. You know, we would go e to the c1 e to the 5t times this vector. It's these guys right here. I'll write this out. Negative I. V is, and then we have that theorem. This is 1, negative I, 0. Okay, but we don't need this one. So I'll say don't need this. Okay, so what I'm going to do on this one, I'm going to go ahead and write out x2 bar, because I'll just assume the x1 bar is going to be associated with that. This is going to be e to the it times this eigenvector. And what I want to do is break this up into an xr bar and an xi bar. So how am I going to do that? I'm going to use the Euler formula for e to the it. Notice this one's a little easier because I think the other one had e raised to the 5 plus 2i quantity times t. So we're not going to have, you know, we have an e to the 0 or whatever. So I'm going to go ahead and write this as the cosine of t plus I sine t. And then this gets multiplied into this one right here, which is 1 I 0. And so what am I going to get here? I'm going to get cosine t, cosine t, plus I sine t, and then the next one is going to be I cosine t, and I'll put it over here. So this is what I mean that you can skip some steps. So this is I times cosine t, and then this is I times sine t. And what is I times I? I is negative 1, so this is negative sine t plus that. And then the last one is 0 in both places, 0 plus I times 0. And so you can see, look what we have here. I mean, we have this guy right here is x r bar, and then this guy without the i's is x I bar. Two independent vectors that will satisfy those guys right there. Okay, I'll put check marks there. So let's go ahead and write out our final answer. It is C1 e to the 5t 0, 0, 1. Plus, okay, these guys are going to satisfy the other CI's, C2 and C3. So this is C2, and then we'll just take this guy right here, which is cosine t, negative sine t, 0, plus C3, and then we're going to take this one right here, which is the sine t, the cosine t, and 0. So that's the deal. When you get complex conjugates, just pick one of them. I usually pick the positive one, and then write out, you know, like in this case it was x2 bar, write out this part of the solution without the CI, rip it apart into two things. Rip it apart into xr bar plus I times xi bar. And then you'll have these two new guys that can go right here, and you have a good general solution. And we use the theory of linear algebra that says that any two vectors that are independent that satisfy this will work for the general solution. So that pretty much covers what I wanted to cover in 9.4. And when we did some of the stuff on the PowerPoint, we talked about the Wronskian of the second kind and all that stuff. We actually covered some aspects of 9.2 and 9.3. Those homework assignments for those are kind of dumb, so we're going to skip those. So what are we doing? 9.4, once again, I wasn't being honest with you at the beginning. This is called vector differential equations, non-defective matrices. And 9.5, which we'll go into next, will be vector differential equations, defective matrices. So this is the order which we're going to do, and this completes the class when we're done. 9.4, 9.5, both of these are actually homogeneous. 9.6 is non-homogeneous vector differential equations, which we'll be doing something called variation of parameters, which is a little different from what you're thinking maybe. And then we come back and finish off doing 9.1, which is a weird place to finish, but you'll see why that's an obvious end point for this class. And then when we finish that, we are done. And this was quite a class in terms of material. Keep up with your homework, don't get behind. Have a good day.